Я бы тебе посоветовал включить не весь экран, не экран стримить, а конкретно окно хрома или чем там пользуешься, чтобы не было эхо от этого, от стрима.
Лучше? Все, сейчас только Chrome стрим. Ой, Chrome, Firefox стрим. Лучше сейчас, да?
Да, все прекрасно.
Все, кайф.
Итак, поприветствуем тех, кто сейчас уже на стриме, поприветствуем тех, кто будет смотреть это в записи. Сейчас, через минуту мы уже должны по времени начать. Так, немного подождем. Люди зайдут. С нами сегодня Максим Маметкулов, middle-разработчик из Церебры, энтузиаст машинного обучения, человек, увлекающийся reinforcement learning и, самое главное, повар. Сегодня он будет проводить лекцию по разработке на новейшем фреймворке от Google под названием JAX. Он расскажет, чем он отличается от PyTorch, в чем его преимущество перед NumPy и в каких, в принципе, сферах лучше использовать JAX, если вы решите начать заняться машинным обучением. Макс, немного расскажи о себе.
Да, всем привет, ребят. Меня зовут Максим. Я предпочитаю, чтобы меня всегда назвали Макс. У меня довольно богатый опыт в машинном обучении. Я пробовал очень много разных сфер, начиная от BCI и заканчивая компьютерным зрением. Кодил на разных абсолютно фреймворках, даже на языках. И вот сейчас ребята пригласили рассказать про JAX, в принципе, про его экосистему, как это все работает, почему это классно и почему это, возможно, какое-то будущее ML. Надеюсь, будет интересно. Надеюсь, попишем немного кода, повпечатляемся скорости JAX, и будет весело. У меня сразу вопрос. Удобнее на русском, на английском? Я просто готовил доклад на английском. Если на русском, то это без проблем. Так, в чате там ребята пишут. Не так много. Тогда, Макс,
сейчас закинул мысль, что онлайн... Сейчас еще пару каналов закину. Человек, люди пишут без разницы, на каком языке. Мне кажется, в принципе, чтобы был охват лучше, чтобы людям было большему количеству людей это было полезно, можешь, в принципе, пробовать на английском. Если у кого-то будут конкретные вопросы, уже можешь на русском объяснять, если кто-то будет не понимать.
Да, без проблем. Тогда что, можем начинать?
В принципе, да.
Okay. So, in today's tutorial, I would say workshop, we'll cover some basics of JAX, the XLA accelerator library. It's made by DeepMind, which is a subordinate of Google, and it's ecosystem for deep learning projects specifically. So JAX, in a nutshell, it enhances equality code, resembles mathematics quite a lot, and emphasizes functional programming that I love. And it definitely is better for some deep learning projects, especially when you are in a research kind of structure. And yeah, JAX can be a good match for you. So the structure of this tutorial will be the following for today. So firstly, we got from the intro, we'll learn why JAX is worth it and why not just a regular PyTorch or something like that. We'll then proceed on to building a simple linear regression with JAX. We'll just like code everything from the bare bones. Then we'll learn about Haiku. It's a library built on top of JAX that allows to configure deep learning projects like some neural nets and some stuff like that. Then we'll build like a hello world in deep learning. Then we'll build a multi-layer perceptron on MNIST with Haiku. Then we'll cover some basic do's and don'ts in JAX, and we'll cover the topic of when you need to use JAX efficiently. Okay, so let's get started. The first question, first and foremost, I would say, why JAX? Why not simple PyTorch or TensorFlow or any other like super duper popular deep learning framework? Well, JAX is a fairly new thing. It came out, I guess, in 2018, 2019. So it's pretty new. And basically, it allows you to use NumPy on devices such as CPU and the GPU. And every code of the NumPy is ported to JAX. It automatically parallelizes the code across devices. So there is a function for that called pmap, and it implements the vector map function. So vector map function is basically when you have an operation that takes a list, and for example, you need to iterate over a list, and like iteration over like a for loops, while loops in Python, they're very slow. You can just vectorize it. And most importantly, I would say that JAX has a just-in-time compilation. For people that are not acquainted with CS a lot, it is when the bytecode is directly compiled into machine code just in time of the execution. So like Python works the way that interpreter just like compiles, interprets the code into bytecode, and then the bytecode is run through like the machine, and just-in-time compilation allows to just even more even lower the codes on the level of the machine language. So basically, JAX also handles randomness pretty much differently from NumPy, and it makes reproducibility faster, easier, and more stable. Because like when you have multiple devices, for example, you have like, let's say 1 million TPUs, and you parallelize your network across all of these TPUs, and you have like all different random states in each of the TPU pod, then it's probably a messy thing to like kind of fix it. So you don't need to handle this kind of a headache in JAX. And it seemed to be a lot of unknown features. Like I talk about them, but they're not still influential about like why do I need to care, why do I need to learn it. So yeah, like if we want to simplify, JAX is like super fast. It scales so much easier, and it allows like any type of modification that's like possible. You can run it on a device. So, okay, let's stop with the words. Let's just run some tests. Here is a simple code in NumPy and simple code in JAX. This code is intended to calculate the simple sum of Hadamard products. Basically, it's like when you multiply each element of the matrix by the corresponding elements of the another matrix. So here is like x plus x multiplied by x plus x multiplied by x multiplied by x. So, and let's take a huge matrix, for example, like 10,000 on 10,000 matrix in a float 32. It should be like pretty much a lot. And let's just time it with the time it function. So it will run through some loops, and you will see the results of like the NumPy execution of this function. Also, to be clear, I do not use GPU in this example, because basically, if I use the GPU, it will be even faster. It would not be a fair competition, because like the NumPy runs on CPU. Yeah, by the time I was talking, the NumPy just generated that it ran about 359 milliseconds. It was a mean from the 7 runs. And let's run the same, but in JAX. So basically in JAX, JAX is actually interchangeably complete with NumPy. So you can use the NumPy functions in JAX, but just like, importing JAX as NP, for example, except any kind of randomness, because JAX takes randomness quite differently. So yeah, here we define the same function like here, fnx. Because of duck typing, we can do it because like we do not need to re-implement the functions, some stuff like that. And we just use JIT. JIT is like just-in-time compilation that I talked before that allows to compile to machine code. And we just like run the same, absolute same experiment. We just wrap this matrix around the JAX NumPy array. And just let's see the results. Yeah, it's always a lot of warnings here, but so yeah, the result here is 77 milliseconds, also the mean of 7 runs. And I guess, yeah, you can differentiate that JAX is way faster. So this happens because of the JIT compilation and because of the caching of some functions. For example, when you have one function that is run several times with the same inputs, it can just like use the cache value. So it makes things things in neural networks, for example, so much faster. And yeah, it's just simply feels like a magic. So yeah, it's obvious now that JAX is way faster than bare-bone NumPys. And you know, however, we have like a lot of this unknown code, like how does this work? What is this JIT and stuff like that? So let's build a simple linear regression with JAX so that we can learn by doing. So we can actually like try to implement something from scratch, and we'll learn JAX on the way. So yeah, first off, let us import all of the libraries that we'll work with. We'll have NumPy because like we need to generate some data. From JAX, we'll use this 4 perfect functions. I will explain in detail each of this function right now and when we'll use them. So JIT, as I told before, is a just-in-time compilation. It's a good thing to just like make your function easier, faster, and stronger. The VMAP is when you have a list, for example, in Python, and you want to just like iterate over it faster, you can just use a VMAP. So it stands for vector mapping, and it basically like allows to batchify any function that you use. Yeah, so probably sound too techy, but it is what it is. So the other function is make JAX PR. It's a good function to just see how JIT functions are traced. So basically, you can just like run make JAX PR, and it will show you how it's traced. So let's just like run an example of it on this function. I guess if you are not against it. Sorry, I will run it in the next cell because I want this notebook to be preserved for you to use later on. So let's just run the JAX fn, and let's just like try to trace it with some, I don't know, let's say x, for example. Yeah, sorry, did I just like miss something? It's a bit callable. Oh yeah, sorry, just like expecting a pure function. I always forget about it. So basically, yeah, it just like shows that here's a fun function that is like traced with JIT here. It's like a Python wrapper around it, and when you have like an input here, you can just like trace it like this. So basically what you're saying is take this function, trace it all the way to like the machine codes on this example, and it just like outputs. Let's take this matrix. Let's call the XLA. XLA is the accelerated linear algebra package for, if I'm not mistaken, C++. And let's call the JAX PR to just like do the multiplication, addition, multiplication once again, and addition. It helps you in debugging the functions that you do not know what they do, like in between, what are they supposed to do. So it's quite handy to use in a kind of environment when you need to learn what functions does. So yeah, let's go back to the simple linear regression example. We'll also use a random to generate the noise. And we'll use the matplotlib's pyplot to generate the plots. Basically, we'll try to learn this kind of equations. It's 2 multiplied by x plus 3. We'll try to learn this coefficient, so it will be our weight, it will be our bias. And we want our weights and biases to be like the exact same values. So the seed will fix to 23, and here's how the randomness works in JAX. Basically, what we do is we call the pseudo-random number generator key, and we pass the seed in it, and then it returns us the key. The key is actually like the seed in the algorithm of generating pseudo-random numbers that allows reproducibility. It allows like extreme reproducibility, and because it's implemented in all of the JAX modules, when you have like a P map, it will be like transferred all the way to all of the devices. So yeah, it's an extreme way to like enable all of your experiments to be the same despite the devices, machines, and everything. So yeah, let's just like have a lint space of 64 points from 0 to 10, equally spaced. We'll then shuffle them, not to make it obvious. Yeah, and then we'll just like add some normal noise and multiply it by a half, just because like normal noise sometimes like it throws out the values of 2 and -2, and it could be quite a lot. So yeah, we don't want too much noise. We want just a toy example so that we can run it and just like enjoy ourselves. And we'll just try to plot the data, the generated data and the true data, to just see that we have actually generated some viable data. So let's run this. Yeah, as you can see, like these are our data points that we generated, and this is like the true data distribution. I guess it looks kind of the same, so I think it's doable. Okay, let's come up to the ML part, to like the most exciting one. We'll first define our prediction function. It will be a function of the inputs and the parameters. We have only 2 parameters here, so it's quite easy. So it's like only weights and biases. Like, for example, if you would have GPT-3, which has, I guess, 100 billion parameters, yeah, it would be quite not handy to just write 100 billion lines of code of these parameters. So we'll have only 2 parameters. It's just like a weight multiplied by the inputs and plus the bias. We'll also define the loss. We will use the standard L2 loss. It's just a mean of Euclidean distance between the true data point and the predicted data point. So we just define it like in JAX functions. Then we want to define our forward function that will make a forward pass and return us the value of the loss. I'll explain later why we do it like in this kind of fashion, because we want to enhance functional programming. We do not want any kind of object classes. We want the function to be pure, and from computer science point of view, it's when the function does not have any side effects. It does not affect any state, like external state of the program. And when you have like only one mapping. In mathematics way, it's just a simple like definition of your function. So you have like one set mapping to another, and that's all. So basically, we want to enhance functional programming. That's why we use functions a lot. We'll take the predicted value of y by using the function that we defined earlier for prediction, and then we'll just return the loss. Okay, let's come closer to the actual calculation. We'll place our initial guesses of the parameters at 1 and 1 points, and we'll write the gradient to be as the accelerated gradient of this function. So, okay, let me just tell you straight away about the grads, because it's probably the most important thing in JAX. JAX supports the automatic differentiation so that you can pass a Python function, and it's using the grad decorator will automatically return you a Python function that just calculates the derivative or the gradient of the following function. However, there are limitations here that you should pay attention to. the grad function only accepts the function that returns a scalar. So there is no way that you can return a vector, for example, and it can take the derivative of it. And if you want to do it, then you can just like wrap the grads around the VMap, so that you can just like map all of the entries to the vectors. And yeah, however, there are a couple of times that you have a need to, for example, train some parameters and you do not need to train another. For example, you want to take the gradients for, I don't know, parameter 1 and parameter 2. You want only them to be trained. You don't want any other parameters. So that there is like an argument, argnums, and you can specify in a tuple the indexes of the arguments that should be taken into a gradient calculation. So here I specified 1 and 2. It's basically our weight and bias, and it will take the derivative with respect to weights and biases and basically like store it in a grad. And we have JIT to just like to speed it up. Yeah. So here let's have a brief recap. We have in the gradients the function that will return us the gradients with respect to a gradient of the loss with respect to weights and biases. It's speeded up. We have the forward function that will return us the loss when we input the input itself, the weights and biases, and the true prediction. The true data point. Sorry. We have the function of the L2 loss, just a simple L2 loss, and we have like the main prediction function. So yeah, let's dive deep into not dive deep. It's not so much deeper, but still, let's just get on the paper the mathematics of all of this what we wrote. So we'll not use closed form solution for linear regression here, however it exists, and you can actually implement it in JAX. We'll instead use a standard gradient update. So we'll basically we have encoded this kind of loss. This is just a standard L2 loss that we have outlined here. And we'll do this kind of an update. So weight will be assigned to the weight minus eta. Eta is the learning rate multiplied by the derivative of loss with respect to the parameter updated. So yeah, sorry, I duplicated this line. However, that's okay. So I just set the eta to be 1e minus 3. And it will just run 3 steps of gradient updates. What we will do is we just like take the dl/dw. It's dl/dw as in this equation, and dl/db is same but for bias from our gradients, and then we'll update it accordingly to the equation of the gradient updates. Then we'll print out the model weights that we have obtained like from the weights and biases, and the real weights. They are 2 and 3, as you can resemble. We just like set them here, and then we'll visualize the real data and the prediction one. So let's run it. Boom. The model weights is 2.108, and the bias is 1.194. The model weight is kind of close to the real weights, and the bias still needs to be learned. But however, on the graph, we can see that we're close. We have made only 30 updates, but we're real close. And I guess it was blazingly fast. Yeah, it's not a really hard computation, but still, like, you know, I still get fascinated by the speed of JAX computations. So I guess it counts. Yeah. So this was a part with standard JAX. Basically, what I wanted to say is that JAX is the best replacement to the NumPy if you want NumPy to be so much faster, if you want to enhance functional programming in it, if you want like to conduct some kind of a research based on like NumPy, then probably JAX is a good way to go. Yeah. Of course, I will share the notebook with you, so you can just like browse yourself with all of this kind of information. So yeah, I guess we can move on to the main Pi, like onto the deep learning thing. So as you can see, like we had only one parameter, like trainable, and one bias, and we still had quite a lot of code in here. And if we have like even more parameters, and it will make it bloated, and we would actually need to track all of these parameters to store the variables in it and stuff like that. We do not want to do this, and I guess the JAX developers didn't want to do it. So they created some of the libraries that just wrap around the JAX and add some modularity to increase productivity with working with neural nets and any deep learning type of shit. So for now, I will answer the existential question, why I chose to use Haiku instead of Flux. There are basically two frameworks that are used on the JAX ecosystem for deep learning. They are Flux and Haiku. Flux is more recent, I would say, and Haiku is like OG one that DeepMind uses. Basically, Flux has a lot of YouTube tutorials on it, and Haiku is like, when you just type Haiku in Google, you just see the Japanese poems. It's currently, like, I would say, super unknown. They still do support it, and I still think it's better. It's much better. So basically, the main reason behind me choosing Haiku instead of Flux is the modularity of Flux. Flux resembles PyTorch. So you can see at the code snippets that it even has an N module in it. It is even like has a function call in PyTorch is forward, and it has like quite a similar signatures like NN ReLU, dances, and stuff like that. It resembles PyTorch so much a lot, and I do not see a point in like giving up functional programming just because PyTorch is so good at like making people happy. Basically, here in Flux, they do not attain to the philosophy of functional programming. So here you can actually modify the external state of the program, and it will be okay. And you can bring in some parameters, for example, like, I don't know, maybe some features and something like that. And it will be good. But I do not like it. Like, if you do functional programming, then it's probably going to be till the end of the project and something like that. However, it still works. It's still viable. It's still super fast, and it's still supported. You can still like use it. For example, if you want to just like transfer your code from PyTorch to like JAX real quick, I guess Flux here could be a really good substitute. So let's just run this code. It just like creates the MLP that takes like this dense layers with like 12 features, 8 and 4. Then just like takes 32 batch of 10 features and just applies. So yeah, I can run it. It still runs. It still like outputs the device array, and everything is in JAX ecosystem. But yeah, everything is not functional programming anymore. We are now talking more about object-oriented because like we have this guy sitting right here. So this class just like ruins every kind of piece of functional programming. So okay, I guess enough of me complaining about the object-oriented programming in Flux. Let's just like go to the Haiku and the Optex. Yeah, Optex is the optimizer library. It's just like ships. The optimizers are shipped separately from the deep learning frameworks. Yeah, I guess it's kind of weird, but still. So yeah, we'll cover the Haiku and Optex in the next following code snippets. So yeah, we'll build Mnist. That's like a hello world in deep learning. We first need to restart the kernel because I don't have enough RAM. Sorry. I guess we don't want me or anybody else to just experience any kind of lags. So yeah. We'll first of all like import the all needed libraries. We'll need a Haiku that is basically like imported as HK. We'll also need the dataset collector. So yeah, here's the catch. In JAX, they do not handle like datasets quite a good way. They basically they basically think that you have a number of NumPy arrays and you can just like sample from them. So in JAX, people still use kind of data set handlers from other frameworks, such as like TF or any other stuff, torch data sets. But in this example, I chose to just follow the Google's ecosystem and just to stay on the TensorFlow data set. So we'll only need NIST, so it's okay, I guess. Yeah, it's a funny fact that like people that develop some kind of super hard and super cool algorithms, they still do not have their own dataset broker. But yeah, it happens sometimes. So we'll also import from typing the iterator and name tuple, because we'll use them to create the class of batches, the training states, and we'll use the JAX JIT and grad functions as well. So, okay, let's execute it. It should be pretty easy. Also, do not be like scared because of this kind of warnings. If you had an experience with TensorFlow, I guess you understand me in the way that TensorFlow just spams warnings every now and then. So yeah, just don't be afraid of it. It's okay. Here we'll just like form the batches. We'll just need an image and a label. There will be a JAX NumPy ND arrays. We'll use the shape of the batch size for the label. So it will be just like a 1 digit, for example, I don't know, 1, then 4, any other like digits. And for the images itself, we'll use the batch size by the height, by the width, and by the channels. And channels here is equal to 1. So and height and width is equal to 28 and 28 respectively. In JAX, for the ease of tracking the state of the training, I guess like a lot of people do it. They just like create a class training state, and like they track the parameters and the optimizer there. So I will track the parameters, the weighted average of parameters, and the optimizer state. So yeah, it's just like the types for now. I guess it's more for the beauty of the code and for the easy understanding rather than like a necessity. And we'll also load the data set as a NumPy iterator, so it can be consistent with the JAX. We'll just like specify the splits, the if we shuffle, and the batch size. And that's all. We'll just like use the simple TensorFlow dataset loads, like the NIST. Like we'll use the buffer size of 10 multiplied by batch size, same seed as before, and use it as a NumPy iterator. Then we'll just map it to our batch, and we're good to go. So yeah, let's execute it and move on to the next part. So in this example, we'll use 3 linear layers and 3 Lewin between of them. As a loss function, we'll basically use mean reduced cross entropy loss and implement the following formula. So it's like -1 divided by n, where n is a batch size. It's a sum of all classes. The yi is the class label, so basically like 1 or 2 or any other digit. And log softmax is just, I guess, you know, the logarithm and the logarithm of the softmax function. And y hat I is the probability. Oh, sorry, it's not a probability. It's the output from the NM. So yeah, the probabilities are done after the softmax is like done. So yeah, for yi, it's now only the output from the neural network. Yeah, we'll like implement this one and go onto the gradient updates across this. We'll go to the gradient updates with respect to the parameters of this loss. So yeah, let's go straight ahead. We'll define the network function to make like a forward pass. It will be like instead of a PyTorch way where network is a class where you define the constructor and the forward function. For the method, sorry. Here you define just a function. So functional programming, any fans, you must be screaming right now. So we'll use the type GNP float 32 because we want all of the computations to be consistent. And we'll use a sequential, same as in PyTorch. Yeah, here it kind of resembles PyTorch. We'll use the flatten to just like modify the height width channels to like be number of features. Then we'll use a linear layer ReLU, linear layer ReLU, and the final linear layer. Basically, one more difference from the PyTorch is that you do not need to specify the inputs of the linear layer. We will do it later, and I will explain why you don't need it. So yeah, then we'll just like compute the outputs by just like passing the object to MLP, and yeah, we're good to go. So then we'll define the training function. We first of all will apply without applying random number generator. We'll transform our net function. So here we basically saying that Haiku, please do not ask us for the key every now and then, and we'll just like use this kind of function, and this will be our transform. So it is kind of a substitute to the constructor of the PyTorch. Yeah. And for the optimizer, we'll use the Atom with the same learning rate as in the first example, 1e-3. And we, as you can see, do not explicitly show the parameters that will be optimized here. Yeah, let's go further and make the data sets. We'll make like two parts of the data set. First of all, we'll make train data set that we'll just like use only for the gradient updates. And then we'll evaluate on the data sets, both on the train data set and the test data set, to like record the metrics of accuracy. So yeah, moving forward, we're going to define a cross entropy loss that I introduced earlier, this one. We'll just like gonna just code it. So we'll use the batch size to like get the coefficient here. Then we'll apply the network. As you can see, instead of forwards or just like calling out the call methods, we just like use apply and we pass the parameters. It's an important thing. We pass the parameters of the network, and then we pass the example itself, and then we obtain the logits from the network, and then they will be sent to the log softmax function. As you can see here, we computed this part of the equation, and here for the labels, we just like one-hot them for the 10 classes. And as you can see, here is the final log likelihood that we were just like writing out here. So this is the log likelihood that we wanted, and we just like do the minus for the mathematical consistency, and we're dividing it for the batch size. So yeah, I guess it should be pretty straightforward. Let's go further to see some JIT accelerated functions. So here we have the accuracy metric. It just takes the parameters, the batch itself, then computes using the network, and then just throws out the logits, and we make the predictions out of them. And we made it JIT accelerated, so it does not produce any side products. It can be accelerated in JIT, and it's safe to use. So we can actually use it easily and speed up our computations. So yeah, let's go further and define the update function. It will be our train step. We'll pass in the state. The state, as you probably can resemble, is the parameters, the average parameters, and the optimizer state. We'll pass the state and the batch. We'll take the gradients. So the gradients of losses with respect to parameters. By using the grads around the loss function. We'll then like pass off the parameters on the batch, and then we'll just like pass them onto optimizer update. So as you can see here, you do all of the things manually, and you control the process. So it's not like building Lego with PyTorch where you can just like buy a keyboard where is a conf 2D and max pool on it, and you can just stack all of these layers. Here you just like modify it from scratch. You can take something off, you can take something in, and yeah, it's quite easy. If you do some math calculation or probably designing a new layer, then it's quite easy and handy to work with a kind of structure. So yeah, continuing on to the update function, we have the updates and the optimizer state returned from the optimizer. So optimizer updates itself with the opt state, and like it returns itself, and it returns the updates itself. So we have to like apply the updates by hand. In that case, it's quite easy to do a gradient accumulation. And yeah, I guess it's a good thing to like notice. Then we just apply the updates on our parameters. We apply the updates on our average parameters, and then we return a train state. So we return just like a refreshed train state after the batch have undergone the gradient step. Okay, I guess it's enough for functions. Let's move forward and like write out the network initialization that traces the image, and we'll write the train loop and the evaluation. Then it will run it. So probably you remember the time that I was talking about that you do not need to specify any kind of an input layer dimensionality in linear in Haiku. Yeah, well, that's because you initialize the layer, the network, with the example. So basically, you trace it, and you can see, and just like the network gets to see that. Okay, I'm getting this shape on this step. I'm getting this shape on this step. That's okay. So the network in it takes the key from the pseudo random number generator key and the example itself. And then we get the initial parameters returned. And initial optimizer state is just like we run the optimizer initialization on initial parameters. So I guess it's pretty straightforward too. We define the first state to be the initial parameters to be like the average parameters, and the initial optimizer state. So I guess this section should be like pretty straightforward. It's just like doing everything from scratch instead of like just calling the super ones. Okay, then we'll define a train and evaluation loop. We'll have the evaluation every 100 steps. So it will be periodic, and we'll have 1500 steps in total. We'll have the evaluation calculated for both the train splits and the test split, and that will be like recorded in accuracy. And for each of the step, we'll do the gradient updates. So I guess we are acquainted with all of the functions that we have talked about. And yeah, I guess the question that arises like the most is like, why do you define function inside the function? Like, is that a bad code practice? Yeah, in pure Python it is. It definitely is if you are not using like kind of decorators or stuff like that. However, in this case, it just forces Python to be like of a nature of a functional programming. So we do not use any class here. We just like use functions. And yeah, it's like Jack's way of doing things. So let's just run this code and let's just like start training. It should train extremely fast, and we should just obtain the accuracy of about 90%. 90, yeah, I guess 1992, something like that. Yeah, sorry, we forgot to like execute here. Yeah, as always, like a couple of warnings from TensorFlow, and every now and then they appear. So the data set is downloaded. Yeah, we're going in. So the first accuracy was like 0.066 on train split, and it's quite low. For the second update on the 100 steps, it's like much more. It's like 0.2 almost. And for now, we should be observing, yeah. So here on the 1500 step on test, we have 0.961. So I guess it's a decent thing. We just like trained the neural network from scratch using the JAX and Haiku and Optax. And yeah, and it's all done in functional programming. It resembles math a lot. It does not have any like classes. You do not need to think about like configuration, production, and stuff like that. So if you're a researcher, I guess you already like it. Yeah, moving on to the more boring part is like do's and don'ts. It's especially like when to like do it, when to not do it. And basically I outlined the do's is when you need some extremely custom layers, for example, you're designing a layer and you need this kind of variability, you need this kind of speed, then JAX is a way to go. It's definitely a way to go. You can modify everything as I just like showed you. You just like write it down anything. The second reason is just when you need a decent speed up in comparison of pure NumPy. I guess we just like ran a couple of experiments to see that it definitely is much faster. And you can even find more evidence on the internet, or probably you can run even more tests by yourself. You also maybe work a lot with a NumPy and you want to accelerate it. For example, I don't know, in some kind of researches, there are like, I don't know, some transformations that are supported by a NumPy and not supported by Torch, for example, and you need to like accelerate it really fast. Then you probably can use the JAX. You can at least look at the JAX. The fourth reason is not like, I would say it's the most controversial one because many RL enjoyers will doubt me in this, but I still think that JAX is the best for using the reinforcement learning, because in reinforcement learning, you definitely have to do quite a lot of things from scratch. It's not usual MNIST or something like that. So when you are writing some kind of an updates, Bellman equations or stuff like that, you probably need to see the math in codes from scratch, from split second. So yeah, it's my way to go with reinforcement learning. And there are packages that support environments, also like gym environments, like a B suite. Yeah, it's behavioral suite, I guess. So yeah, and like the last but not the least, I would say even the most significant one, that you love the idea of functional programming. You love the idea of just like throwing the OOP out of the window and not care about some kind of production thing setup and reproducibility from beneath the team members. Yeah, I do have a sympathy for the functional programming paradigm, because it's quite, I would say, descriptive, and it resembles math a lot. Because like the main object in math and then functional programming is functions. And the definition of function and functional programming and math, they do look kind of the same. They do have the same constraints, and it's not your like definite easy function from programming where you can do whatever you want. So yeah, about the don'ts, I would say that there are only 3 reasons that you do not want to work with JAX. The first one being like you're a complete beginner in deep learning or scientific computing and any other field that requires NumPy. I guess you guys are not complete beginners, so yeah, I guess it will be useful to you. Why do I think so? Is because you can mess up easily. You can mess up with some kind of a parameter, a bug, something like that, and it will take you a ton of hours to just fix the bug. And I do not think it's a productive way to start your journey in deep learning, because like it's so much more than just like choose like your choice of framework. So yeah, and also the second don't is when you are a beginner with a Python. So in Python, you need to understand how function works, how decorators work, how, for example, tracing works. But like in Python, the tracing is not done on the side of Python, but still. So you gotta be super super advanced, I would even say. Yeah, in Python, you gotta be on a good terms to actually master JAX, because yeah, it's quite hard, and sometimes like the errors that are thrown, they are not easily tractable, because like they are traces from C++ or any other languages that is LAX run on. So yeah, and the third don't is when you need a fast prototyping and you work with like super popular architectures and layers. For example, I don't know, let's just assume that you work on the cutting edge bleeding research in computer vision, and just like ConvNext just came out, and it's not yet supported on Haiku or even on Flux, but it's already in Torch. then you can just like use storage, and it's probably better for you and for your research, of course. Yeah, this were my like do's and don'ts from my own experience, from experience of like talking with other people that use JAX a lot. And let's move on to like when to use JAX efficiently, when you can just like say it's JAX time. I would even like specify the first reason of the parallel computation. I want the nodes and the servers, graphic cards, CPUs, anything to be the main reason. So in PyTorch, you need to write the DDP. It's like distributed data parallel in order to run something on multi-nodes, multi-GPU setup to run it efficiently without any bottlenecks. In JAX, it's just a simple PMAP. Yeah, I'm sorry that I do not have like 2 or 3 graphic cards to just show you how it works, but still it works. The second reason is when JAX is a way to go is that you work with a TPU. So JAX has been developed, I would say, in parallel with development of the TPU chips, and it's probably the most optimized for the TPU. So if you're using TPU, either way, like, I don't know, on Kaggle, on Google Colab, anywhere, JAX is a way to go. And the another reason, and it's probably not a good reason, but still, is that you have a lot of Pythonic loops in your code. You have like a lot of for I in range something. Then you probably want to speed it up, and you can use VMAP in that cases. Why it's not a good reason? Because right now there is a VMAP in Torch. There is a VMAP support in Torch, so you probably can still use Torch, and it'll be pretty good. Yeah, we have come to the conclusion of my small workshop on this kind of environments on this ecosystem. So yeah, I'll be happy to answer any questions if there are any questions. Yeah, thank you for your attention. Am I still on? Yeah. So yeah, maybe I should. Yeah. I don't know, guys, if you have any questions, just like, is the thing to like raise a hand and just like ask. So are we done, or? Yeah, I don't know. What am I supposed to do? I can't hear you. You are muted.
Yeah. We also had our stream on LinkedIn and on Twitter, and on LinkedIn, he was viewed by Dmitry Hizburin, who is principal engineer at Huawei. He enjoyed your lecture. Now, Big Vlad asks if you can share the notebook. I think we can share the notebook on our channels on gdc.nu in Instagram. We can add a link, and we have our Telegram channel, gdc_nu. We'll share the notebook there. And the recording will also be available with the same link as the live stream.
Yeah, so if there are no questions, then probably you know where to find me. I guess you always can just write me in the Telegram messages and just like ask your question about the JAX or any kind of like framework that I just presented. And yeah, we'll of course share the notebook. We'll of course share like the edited notebook, so you can just run it yourself. However, there are no dependencies included, so please work it out on your own, because I use Docker. And yeah, I can attach like the Docker file for you if it's not like if you're not that familiar with Docker. So please take some time and be acquainted with Docker because it's a great technology. Yeah, I guess that's it.
And that's it. I just want to say, if you want to get into data science community of Kazakhstan, you can join our Telegram chat. It's telegram.me/database_bot. We have a question. Is it possible to use parameters of Torch models in Flux or Haiku?
No, definitely not, because Torch does its backwards in completely different way. And you cannot use it. And I guess if you can load the parameters, like if you mean the state dict, then you probably can input the parameters from Torch to JAX, but you need to write your own kind of a converter. So yeah. I guess I need to like pause my stream because it's like an endless cycle in here. I don't like it. Yeah. Much better now.
Yeah, I guess that's it. So goodbye, Max. Thanks for your stream.
Yeah, guys, thanks for attending.
Having you here.
Yeah, thank you. Yeah, thank you guys for attending. Thank you for organizing such a great event. Yeah, see you soon.
Bye.
Okay, bye.